All right, back to work. We're going to quickly remind ourselves of where we're at. We're using our example one-dimensional group right now. I'm actually going to do another example right on the heels of this with a more sophisticated group, geometric group, and more sophisticated Lie group. But let's just finish up what we're doing here. This is our transformation equation. I haven't bothered to write down the group expression because we haven't actually worked with that much yet anyway. And we have the parameterization for our shifts and scales. What I wanted to show was we demonstrated how we can find, for an arbitrary function f of some member of the group in some reference frame S, which means some basis which yields a certain set of coordinates for x, that if we change to a new basis, S prime, meaning we shift and scale the basis vectors, we end up with new coordinates x prime. And what we're interested in, what is the form of S on the new coordinates? What is the form of this function? And from that we learned basically how to construct it for infinitesimal transitions from one reference frame to another. But now we want to talk about finite transformations. And the secret here is very straightforward. A finite transformation is a limiting procedure of an infinite number of infinitesimal transformations. And we demonstrated that earlier when we talked about the connectedness of a Lie group, right? So when you have the origin, which is where the identity lies, this is the manifold description of the Lie group. We know that any finite operation, so this beta is some finite scaling alpha 1 and some finite shift alpha 2, as opposed to some infinitesimal scaling and some infinitesimal shift, which would have these deltas in front of them. But you can always get there, and we showed how every step of the way you could work with something very close to the origin. So it's an infinite number of these. It's a limiting process. And we have to study that limiting process, which is actually pretty trivial, and it's all basic calculus, but it's that basic calculus that causes, again, eyes to gloss over and people don't remember it. So we're going to kind of walk through it a little more carefully right now. So in other words, in particular, we're going to try to understand this thing. E to the minus alpha 2 d by dx, where all of this is in the exponent of an e. So we have this operator and an exponent of e. We got to understand exactly what's going on there and why that notation is used. It's a certain amount of it is formalism, but it must be understood. So let's begin. So this first, we're going to start with just your basic Taylor series. I like to go back to the earliest stuff we can, right? It provides a certain degree of comfort because everybody who's working this course should say, oh yeah, that's the Taylor series, I remember that. And it refreshes these elementary things that we don't necessarily revisit on a fundamental level each time, but this is the Taylor series. And I've written it in a slightly suggestive form because I've taken the derivative out, the nth derivative, right? This goes n equals 0 to infinity. I've taken that derivative out and made it look a little bit like an operator acting on f of x, because of course that's sort of how this stuff rolls, is we separate that derivative out and we're creating differential operators. So I've written it in a suggestive form that way. But this is your basic Taylor series definition. So our next step is to say, well, wait a minute, what about f? Let's operate this thing right around b, some number b. So we're going to basically shift the function that we're interested in. But the shift is actually very easy because the only place that it matters is right here. Right? This shifting of the variable here doesn't affect the derivative of x of f of x with respect to x. So we can rewrite this incorporating that shift. And so here I've written that in. This, by the way, just as a reminder, of course, this evaluation at x equals a is just for this part, right? Just for this part. There's no way to really capture that. I guess the way it's usually captured is by having it look like this, so there's no doubt about what is what. Interesting. Maybe I should do that. Why don't I write it like that, perhaps? Yes, but now that I've gotten started, I've got to fix it everywhere, right? So let's fix it here and move this over here like that. Okay, so let's try that notation. This is just all that was done just to eliminate the possibility that you might have made the substitution x equal a in here, where it obviously doesn't belong. And of course, I have forgotten the 1 over n factorial, right? 1 over n factorial, that belongs in there. Silly me, that was a big mistake. But there it is, it's fixed. And now let's proceed. So for a function that's analytic, you can choose a to be anything, right? An analytic function is equal to its Taylor series, and it doesn't really matter what a is. And we're not approximating this Taylor series, we're keeping all of the terms. So let's choose a to be x, right? This is standard fare in calculus. That's how you identify the Maclaurin series, is you just set a to be x. And when you do that, this goes away. And now we take all of the things that involve n and bunch them together. And as such, we write this. Now this doesn't depend on n, this operator does. So we can split this off and turn this into a sum that's going to be a long sum multiplied or operating on this function f of x. And that sum, of course, is the Taylor series for e to the x. So we end up writing, and I'll put the last line here in red, this we write in shorthand as e to the b by dx of f of x. Right? So now we have f of x plus b. So the shifted form of the function is this operator, which is shorthand for this sum, operating on f of x. And it literally is an operator because this sum, of course, is blown up into, 1 plus b d by dx plus 1 half b squared d squared dx squared plus 1/6 b cubed third derivative x, right? And then this will be, and then times, et cetera, times f of x. So that's a totally doable operator, right? This sum completely is a logical linear operator acting on a function. And this literally is the Taylor series for e to the x if we replace x with b times this little operator, right? So I guess you could argue that this is purely a notational thing because this sum is what's operating, but that sum is equal to its, the Taylor series of this exponential. The exponential is entire, which is a way of saying that it's equal to its Taylor series everywhere on the real line. It's also equal everywhere to its Taylor series everywhere in the complex plane. It's an entire function, even in terms of a complex variable x. So it's a very robust function. So it's fine to write it this way. And so we have this is the way we write down the operator acting on f of x. But the key point is the shift is equal to this kind of object. Now, why is that important? Well, it's important because when we go back to our infinitesimal shift, right, we now can say, well, what about a finite shift, right, where it's no longer delta alpha 2, it's now just plain old alpha 2. Well, the way we create the delta-ness of this alpha 2 is we take alpha 2 and we divide by n and we raise to the nth power and we take the limit as n goes to infinity. So when n is large enough, no matter how big the shift, this term here, the term in front of the generator, this term here is always going to get smaller than any arbitrary number because that's what this limiting process means. N gets arbitrarily large, which means alpha 2 over n gets arbitrarily small, which puts it firmly in the range of the of our ability to consider infinitesimal transformations. And we just do n of them, and we walk our way all the way out to the finite transformation. And so now you look at this and you just see that this is being bundled up exactly the way we bundled it up, where we end up with 1 over n alpha squared right? 1 over n alpha squared x prime minus c squared. Remember, this is our function this is the function f of x prime, right? The 0th order function version. It's still 0th order, but now we've got this guy in front of it, and let me do all these erasures here. And we write that as the exponent of, well, we rewrite it in this nice little neat notation, and we end up with exactly what I just showed you, which of course is a finite displacement by alpha squared, where alpha squared is playing the role of b in this exposition. So that's the point, and he writes it this way, simply as Taylor's theorem. I don't think it's that simple. I had to go back and review Taylor's theorem and figure out how this was supposed to work, but it is in fact elementary calculus, right? There's no way around that. And he does it again over here, right, where now this time it's alpha 1. The generator is now x prime delta x, right? So this is a different kind of process. This is a scaling. So I guess it's worth looking at that. So I found this nice little demonstration of how scaling will work. So now we're looking for f of xa, and this won't involve Taylor series right away, but it will involve this final result. That's why it's a nice proof, because I don't have to sort of start from the Taylor series to get to it. I can actually just broker this fact here. So it's a nice little exercise, right, like that. But we're interested in the functional form involving a shift, right, a shift of ax. So we write that as f of e to the ln to the log of ax, and then f of e to the log a plus log x. Then we're going to call log x y. So we'll write f e to the log a plus y, where y is defined as the natural log of x. That's just a convenient little variable name, so I don't have to keep writing log of x. The 3 equal sign means it's a definition, not some sort of important equality. So this is our expression of a shift, right? This exact shift is literally written this way, so we've done very little real mathematics. And now comes the clever part. What we do is we define g, right? G of say b is going to be equal to f of e to the b, right? And therefore, this function here, this is a definition also, right? We're just defining g of b that way. So this guy is actually equal to g of ln a plus y. So if you look at it, you can kind of see where we're going. We've got this shift here, and using this little logarithm stuff, which always takes products and kind of converts them to sums, and then by defining this new function, what is a shift to the function f, what is a scaling to the function f, right? This is a scaling, not a shift. So the scaling of the function f ends up over here, but what is a scaling to f looks like a shift to g, right? If g is understood to be as a function of y, right? And in here that's the case. F is now a function of y, where y is defined this way. So that's why we've made this substitution, but that's also why we define g. So we have a function where scalings look like shifts, and we already kind of know how shifts work. But we're not quite done. So now I can write down that this shift is this shift operator, right, by a shift of ln a. ln a is the natural log of a is the amount of the shift. That shift operator is right here acting on the function g of y. There's actually a little bit of a less ambiguous way of writing this, is have the operator acting on the function first and then put the variable at the end. So it would be e ln a partial y, where I'm creating a new notation where partial y equals b by b del by del y, right? So little convenient notation. That operating on the function g, right? And then this is understood as a function whose independent variable is y, right? That's another good way of looking at it. But then the e to the ln a, you can actually take this quite literally, right? This whole thing can be now worked literally. That's why this notation is so useful, is you can actually use the rules of exponentiation here without any trouble. E to the ln a is simply a, right? So this is going to be a to the partial y operating on g of y. And you're getting a little bit away from the Taylor series, but this is still just a Taylor series here. But now that Taylor series is represented by this object, where we just kind of simplified the e to the natural log of a just to be a. And now we just go back and start reinserting our functions f and ln x, right? So how would we do that, I guess? Let's see. Hold on. You would go, this is a, the partial of y is now partial ln of x, right? So it's obviously the chain rule is going to be involved there because we're taking the derivative with respect to a variable that is in itself a function of another variable. G to the y is actually f to the e y, right? But y is ln x, right? So this equals a to the partial ln x times f. See, that is ln x. So that's really f of x. So let's see, how do we think about this guy? How do we think about partial ln x? I think, let's see, we go partial ln x is defined as the partial derivative with respect to ln x. And we want to think of this in terms of a derivative of just x. So that has to be this, right? It has to be, this is what cancels for the chain rule to work, right? So you have the partial derivative of x with respect to ln x, and then you have d by dx. And this is just the reciprocal of the derivative of ln x, which is, the derivative of ln x is 1 over x. So this becomes x d by dx. Phew. So this guy here ends up equaling a to the x partial x of f of x. And the whole point was that equaled this guy up here. I'll do it in red so you can see that I'm moving my pen. So that has to equal f of a x. Okay. So now in our case, a is e to the alpha 1. So this becomes e to the alpha 1 x partial x of f of x. Okay. And that is, so this now is the operation of the shift, where the only difference is the insertion of that little x there, right? So that's now not a shift, the scaling. So the scaling involves the same operator really, but you get this little x in there. And again, this ultimately is to be thought of as the sum from n equals 0 to infinity of alpha 1 x partial x, right, to the n over n factorial, right, like that. Okay, let's see if this marries up with what he did here for these displacements. So he does it right here. His scaling is done up here, and so I mean, we know this is the x. Oh shoot, this is so fat. We know that the generator for x1 as a function of x prime. Notice, by the way, that, I'll say that in a moment. We know that this is equal to this guy right here, right? and look at it, it's x prime del x prime. So that's certainly, and then this is your small factor in front. So it's certainly a shift, A1 over n. So that's definitely a shift. So this becomes, let me see, there's something missing here, isn't there? What is it? Oh, no, this is fine. This is the definition of the exponential, right? So that's the definition of the exponential of this object straight up. And once you have the exponential like that, you recognize that this is the shift operator, right? Just that's what we've done. That's why I did this, right? I did this so when you saw this operating on a function, you would realize you're just dealing with the shift of the function. And he sort of skips all that. He assumes you know that. And, I knew that once, I'm sure, but I had to remind myself, of course. And so now, I keep saying shift, scaling. You have to remember that this is the scaling of this function, and that scaling just applies straight up to the x variable, right? And so there you have it. There's the finite scaling, which is exactly what we expected it to be. So that is how the finite versions work. So this has exploited a couple things. The first thing we did is we went back to fully understand what a generator was. And that definition applied to anything that was a Lie group of transformations. Now, this idea of a generator was introduced based on the principle of taking a function that belongs to this underlying geometric space, a function on that underlying space, and finding the new form of the function after you transform that space using a member of the Lie group of transformations. So that's what the generator was to us. The funny part about all this is that these generators very quickly take a life of their own. And very rarely in physics do you actually go back to the group, the underlying group that's transforming the space. But what you do always do is you keep a good eye on the generators of this group. They come together and they're going to form what we're going to call a Lie algebra pretty soon. And those generators almost describe the group so completely that you almost never think of the group. This idea of, we're going to translate and we're going to shift, that's very contrived little mathematical problem that we use to sort of illustrate how these generators actually generate these rotations and translations that ultimately generate these finite, where's my page? These finite shifts and scalings in this particular case, but they could also define infinitesimal and finite rotations, for example. But a lot of the groups used in physics, there is no obvious intuitive idea of rotating or shifting or scaling. The groups that are relevant are groups that have no real foundation with intuition at all. And that's where things become deeply abstract. But even in those cases, we tend to stick with just working with the generators. And this is one of the reasons why this subject can be really confusing, is in physics, especially if you approach it from physics, you're introduced to the generators right away. There are approaches to quantum mechanics. In fact, every approach to quantum mechanics I've seen just jumps right into these generators as the generators of the group of rotations, but they never really describe the group of rotations because you don't need them. You only need the generators. So they teach using the generators as a tool to understand the quantum mechanics of angular momentum in particular. But so the purpose of my course is to go back to the basics, to really link these generators up deeply with the Lie groups. And Gilmore is very serious about this. He starts with studying the groups, and then he says, these groups can be associated with generators. And slowly, though, even he will end up working almost entirely with these generators. And that's a transition from Lie groups to Lie algebra. And the reason it's called algebra is that these generators themselves, these xmuth objects, right, x1, x2, x3, all the way to x eta, where eta is the size of the manifold of the underlying group, right? These x eta objects will form, generally speaking, the basis of a vector space, which is also an algebra, right? So it's a little bit more complicated than a vector space. And that algebraic structure, which is called an algebra, that becomes the foundation of all of our work. So we've learned how to calculate the generators for anything that is a Lie group of transformations. Because remember, the generators were all built off of F, right? No transformation. If your Lie group is not a Lie group of transformations and you have no F, then you can't calculate a generator. So in our next lesson, we are going to overcome that problem. It's a kind of a trivial overcoming situation, but any Lie group with as transformations or not will have generators, and I'll show you why. And then we'll do one other quick example of calculating some generators for one other group that's not in Gilmore's, not in this book of Gilmore's at least, just to give a good example that has a little bit more dimensionality in the geometric space. Give us some more, give us one or two dimensions other than just this one. Okay, all right, so we'll see you next time.